All right, today's the 28th, I believe. Okay, so I think everybody should be done with the quiz at this point. I didn't want to actually make a change to it while folks were working on it in case it actually kicks anybody out, but I'm going to go ahead and publish our changes. Now everybody should be pretty much done. So now we're good. All right, so just a few things to think about here, guys. Moving forward, I was looking back at the grade book here just to kind of see where we were at this point in the semester. So we've got roughly 2 weeks left. So in terms of quiz points, we're in pretty good shape. So as of Monday, we had 25 for 5 quizzes. So that's enough to get us to the 100 points that we need in the syllabus. And as of the last Friday quiz we have, that gives us 10 Friday quizzes, which is enough to get us to the 200 points we need in the syllabus. So here's what's going to happen. We'll have a Friday quiz day after tomorrow, like we normally would, and that's going to be an extra one for you. So you guys remember, I promised you an extra one to help make up for one that maybe you missed or that you didn't do well on or something like that. So we'll do that on Friday. So that's an extra one. And the other thing I think I'm going to do is I'm going to keep on giving us 5 for 5 quizzes as we move through till we get to the end of the course. And I'm going to let those just kind of be extra points for you. So you have the opportunity to get some extra 5 for 5 points here. I'm just going to add them in just like their regular points. And they're only there to help you and not hurt you. Okay, so in other words, I'm not going to increase the total required points in the course. I'm just going to let these other 5 for 5s just add to your point total. So they can't hurt you. They can only help you. So again, if you missed some 5 for 5s or did poorly on some, hopefully doing a few more will help to make up for that. So if you're kind of one of those folks that's like on the edge between, say, a D and a C or something like that, focus in on these last few days and make it count because you've got the opportunity to get some extra points here. All right. Now, the other thing that's probably worth mentioning to you guys is that we're probably going to finish a tad early. Again, I've got 2 weeks of class left, and I don't think I'm going to need much more than about a week and a half to finish up the material I want to deal with. So we actually may end up finishing a couple days early before the end of the semester. So hopefully that's okay with everybody. I can't imagine anybody would have a problem with that. But I think I'm going to content-wise get to where I want to be. All right, so I'll let you know about that as we move forward. But it may be that we get to week 14 and we may only have to meet on Monday or something like that. So that would be kind of nice. We'll just see how it goes. The other thing just to mention to you guys is that we don't need to watch a video for Friday. I want to kind of hover on Lewis structures and some of the intricacies of Lewis structures before we get into molecular geometry, which is kind of the next thing. So don't watch a new video for Friday. If you want to, go ahead and do it, but you don't need to. All right, so the next new video will be for Monday's class, and that'll be molecular geometries. So we're kind of finishing things up. We're kind of wrapping things up here. So what I thought I would do here before I hop into the notes is jump out and just talk a little bit about Lewis structures. Let me pop into Chem 101 here, see if I can find it. There it is. Okay. And let's just take a look. I was kind of looking at some of those quizzes that we were looking at. So let me see if I can find that quiz that we were doing today. So that was 428. Sorry, wrong quiz. Okay, so here we are. And I saw some kind of interesting answers popping up. So let's just take a look at number 1 here. And here's what the results look like. Obviously, it's not showing you who did what, but these are the results that we got. So 25 folks, actually, out of about the 30 who took the quiz, got that one right. But if you look down, for example, at the third choice down there, it's just kind of interesting. Time's up, so we're done. So if you actually look up there at the third choice that we have, what you're going to notice there is that it's kind of an interesting structure, but why could we say that's the wrong structure? Okay. So it's, again, not picking on the 2 people who chose it, but, why would we actually say that would be an incorrect structure? What do you see there that looks a little out of kilter? I mean, there's something kind of jumping right out at me that just, says, oh, that's not where we want to go. Anybody want to guess what that is? Looking at that third structure down.
Hydrogen has 2 bonds.
Yeah, that's exactly good. Look at that hydrogen in the middle, okay? So hydrogen can never have two bonds to it because remember, hydrogen only takes a duet of electrons. And in this structure, we've assigned it 4 electrons, right? Through those two bonds. So we can't do that with hydrogen. So it kind of goes back to one of those rules of Lewis structures that hydrogen always has to be an outer atom. Okay, so carbon's going to be in the middle. We'll put hydrogen on the outside and we'll just attach bromine to it as well. Okay, so that was just kind of an interesting structure I thought that popped up, and I just wanted to make sure everybody could understand why that would be an incorrect structure. So the other thing I want to do just as we're messing around with this is I want to practice a little bit before we jump into some of the exceptions. This is, let's see, here we go. Lewis structures part 2. I've got 12 minutes assigned to this. And it's just playing around with the Lewis structures a little bit more. So let's play around with this. So if I come in here, we can actually see it's just a few little problems. And this is going back and looking again at simple Lewis structures and letting you practice a little bit again with the app that comes with Chem 101. So play with this a little bit and then we'll swing back around in about 12 minutes and we'll talk a little bit more about exceptions. I told you we'd be practicing today.
How can iodine have more than 8 valence electrons?
Very good question. That is going to be an example of one of what we call an expanded octet situations. And the reason for it is because iodine is in or below row 3 in the periodic table. And what that basically means is that we have some nearby d orbitals we can put those extra electrons into. So we're going to actually swing back and look at that one as an example. You're going to find the same true with the xenon difluoride in problem 4 also. All right, folks, so let's go ahead and take a look at a couple of these exceptions. And a couple of them did actually show up on this, so you've had a little bit of exposure here. So one option we have is the so-called expanded octet. And what this means is that we're talking about an atom in the Lewis structure that's going to take more than 8 electrons. Now, normally that expanded octet is going to be on the central atom. All right, so what this sometimes means is that we're going to get a funky formal charge, and we talked about formal charge in last night's video. And if we have to get a funky formal charge anywhere in the molecule, it's going to be on the central atom. So let's take a look at the I3 minus. Okay, so that was one of the ones that you guys had in the practice that you just did. So let's calculate how many electrons we've got. So iodine is over in group 7. 3 times 7 is 21, plus an extra one for the ion is 22, right? I'm doing all this math in my head, so make sure I'm okay. 3m7 is 21 plus one more is 22. Good. All right, so basically what I'm going to do is I'm going to put an iodine in the middle, and then I'm going to put an iodine around the central one. Next thing we do is we start making bonds. So we go 1, 2, 3, 4. Then we go to the outside atoms, right? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then I go to the central atom. 17, 18, 19, 20, 21, 22. Okay. So if you look at what I've got here, I'll go ahead and put a 1 minus on this to show that it's an ion here. So if you look at what I've got here is each of the outer iodines has an octet, but look what's happened to that central iodine. Go ahead and count up what it's got. It's got 1, 2, 3, 4 from the bonds, 5, 6, 7, 8, 9, 10. So we're 2 beyond an octet here. Okay. Now, can we get away with this? Well, it turns out, yes, we can, because there's a rule for this. So when we talk about expanded octets on the central atom, here's the rule. The central atom has to have, or it must be a nonmetal in at least row 3 of the periodic table. Okay? And the reason for this, as I mentioned just a little bit earlier, is because that gives us access to d orbitals. And those d orbitals actually lie close in energy to the p orbitals that we've been filling, okay, to get to that particular element. All right, so basically we've got empty orbitals where we can put those extra electrons with a fairly small energy cost. Okay, so that's why we can get away with this. All right, so having that central iodine there take more than 8 electrons can happen. And that's because iodine is in or below row 3 in the periodic table. Okay, we have a place to put those extra electrons. All right, so as I was watching this, I noticed that a few people were tempted to put double bonds from the outside iodines into the central iodine. Why would we not want to do that? Well, that turns out to be a formal charge situation. Okay, so let's just go ahead and calculate the formal charge on the outside iodine. So it's how many electrons the iodine brings to the table, which is 7, minus how many it lays claim to, which is 1, 2, 3, 4, 5, 6, plus 1 in the bond is 7. So I have a formal charge equals to 0. Now that's going to be true in both of these outer iodines. Okay. Now, as we said, if we want to actually, and what's going to be the formal charge on that central iodine, by the way? Okay, it's how many the iodine brings to the table, right? Which is, well, I should say it normally has, which is 7, minus how many we said is actually around it. 1, 2, 3, 4, 5, 6, 7, 8. Did I do that right? 1, 2, 3, 4, 5, yeah. 7 minus 8. So I'm actually going to get a -1 formal charge on that central iodine. But that's okay, because we can dump a formal charge on that central atom there, and that's going to be okay. All right. But what if I made double bonds? If I made double bonds, we're going to foul up the formal charge on the outer iodines, okay, which isn't really going to help us out. Okay. We could say that it's a acceptable Lewis structure, but it's not going to be the best Lewis structure. What's the other one we had there? It was the xenon difluoride, which looks like that. Okay, so let's figure out how many electrons we have. Xenon's bringing in 8 electrons. Fluorine is bringing in 2 times 7, which is 14, right? Is that 22? Yeah, that's 22. All right. So xenon's got to go in the middle. Okay. Fluorine on either side of it. Make the bonds. 1, 2, 3, 4. Go to the outer atom. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So it's actually a very similar example to the I3 1 minus. Okay. So now, again, we don't want to make double bonds here because the fluorines are going to be happy with their formal charges as they are. Okay, they act like the iodines here. So we've got a formal charge equal to 0 on that fluorine. I've got a formal charge equal to 0 on that fluorine. What about the xenon? Well, that's going to be 8 electrons minus 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 minus 8, which is 0. So that looks good all the way around. So again, if we try to put double bonds in here, we're going to foul up those formal charges, which we don't want to do. Okay. So again, we're looking for the best possible energetic Lewis structure here. So we can always go back to formal charges to look at that. All right. Everybody okay with that? Now here's another interesting one. I have it in my notes and we'll do it. It's the sulfate ion, one of those polyatomics, SO4 2 minus. Okay, so let's look at that. Sulfur's bringing in 6 electrons. 4 times 6 is 24 on the oxygen, plus 2 from the ion, right? So it's 24, 25, 26, 32. Did I do that right? Yeah, I think that's right. All right, so the sulfur's got to go in the middle, right? And we'll surround it by 4 oxygens. Okay, make some bonds. 1, 2, 3, 4, 5, 6, 7, 8. And we go to the outer atoms, right? 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so if you look at that, and we'll go ahead and put our 2 minus around that to show it's an ion. Is that an acceptable Lewis structure? Well, sure. Everybody's got an octet, right? The sulfur's got an octet. All the oxygens have an octet. It's happy as a Lewis structure. But here's the question. Can I do better with formal charge? Let's take a look. Let's look at the oxygen. My formal charge there is 6 electrons that the oxygen brings in minus 1, 2, 3, 4, 5, 6, 7. So that's going to be a -1. And that's going to be true on all of those oxygens, right? Now let's look at the formal charge on the sulfur. Sulfur brings in 6. And I want to subtract, cleaving the bonds 1, 2, 3, 4. Okay, so 6 minus 4 electrons. Ooh, that's going to be a +2 formal charge, right? So if you look at that, that's pretty nasty. We don't want a +2 formal charge on that central atom if we can help it. So do you see a way in which we can minimize the charge on that central atom? In other words, if I have a +2 formal charge, I got to get that thing more electrons. How could I get more electrons to the sulfur? What are my options for doing that? I can't bring in any more, right? I've used up all of my electrons that I have available to me, but what's another way I could get some more electrons to the sulfur? How about a double bond, right? If I, for example, bond in there and bond in there, that's bringing, in each case, an extra electron to the sulfur. So now what I have is something that looks like this. Now, it's still not a perfect situation because I'm still going to end up having a -1 on 2 of those oxygens. But look what's happening here as far as the sulfur goes now. My sulfur's formal charge is going to be 6 electrons minus 1, 2, 3, 4, 5, 6. That's going to be 0. That's good. Now, what about those oxygens there with the double bonds? Okay, how about their formal charges? So let's just do that oxygen right there. Let's see, each one brings in 6 electrons. All right, and then I can do 1, 2, 3, 4, 5, 6. So it looks like I've minimized formal charges on the sulfur and 2 of the oxygens. I've still got a formal charge of -1 on the oxygen up there and also on that oxygen there. So I really can't do any better than that. I can't get all the way to 0. But what I can do is minimize formal charges on 2 of the oxygens as well as the sulfur. And I can put those double bonds in there. Now, do I get an expanded octet when I do that? Yeah, I do. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons around that sulfur. So I have an expanded octet, but sulfur's in row 3 of the periodic table. So I have those d orbitals I can place those extra electrons into. Okay, so I can get away with that. So here's an example of how I can take an acceptable Lewis structure, which is the first one up there where everybody's got an octet, but I can make it better by minimizing some formal charges by throwing in some double bonds to that central atom to get it the electrons it needs to be able to get to a formal charge of 0. All right, so again, this is just where we can play around with these things and try to get the best possible Lewis structure that we possibly can. All right, so that takes care of expanded octets. There's one other thing that I do want to mention here, and that's the incomplete octet. So that's the opposite situation. That's where we have a central atom that doesn't have an octet, okay? Now, there's a very specific example that every textbook uses, and that's boron. So almost always when we see the incomplete octets, it's going to involve boron, all right? Boron's a funny a funny atom. Now, here's a good example of it. This is a stable compound, BH3. It's called boron trihydride. Let's draw a Lewis structure for it. So boron's going to bring in 3 electrons. Hydrogen's going to bring in a total of 6 electrons. Okay. Oh, sorry, 3 electrons. What am I thinking here? So 3 and 3 is 6. So I have 6 electrons total to play with. Okay. So boron goes in the middle because hydrogen can't. So I put my hydrogens around the boron here. Make some bonds. 1, 2, 3, 4, 5, 6. I'm out of electrons, right? No more electrons. So I can't make any double bonds because there are no lone pairs or non-bonding electrons on the hydrogens. So where am I? I'm in a situation here where boron is only going to have 6 electrons around it. And it's actually okay with that. Let's calculate a formal charge. Okay, so on each of these hydrogens, it brings in 1 electron minus the 1 electron it brings to the bond. So that's a 0. Calculate the formal charge on the boron. What does that look like? Boron's in group 3, and then it has 3 electrons around it if we cleave the bonds. So I get a formal charge of 0 on the boron, even though it doesn't have an octet. So it's actually fairly happy that way. Okay, and we can make the same argument with another molecule that's very similar to this. This is BF3, boron trifluoride. Okay, so boron's going to bring again 3 electrons in. Fluorine's going to bring a total of 21. So I'm going to end up with 24 electrons to play with. Okay, so what am I going to do? I'm going to put boron in the middle, fluorine around it, make the bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 around the fluorine. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'm good. Okay. Now notice again that we have an incomplete octet on the boron. Now what you might be tempted to do would be to make a double bond from the fluorine to the boron. So let's check formal charges here as we are. Boron is 3 minus 3. That's a formal charge of 0. The fluorine is going to be 7 minus 1, 2, 3, 4, 5, 6, and cleave the bond is 7 is 0. So we're 0 all the way around here. If I made a double bond, let's just do it to that fluorine over there. Try to get an octet. Okay, over to the boron. What's going to happen to our formal charge on the boron now? Okay, boron's bringing in 3 electrons, and now count them up. I have 1, 2, 3, 4. That's going to give me a -1 formal charge on the boron. What about this fluorine over here? What's it going to do to that? Fluorine's bringing in 7 electrons, minus 1, 2, 3, 4, 5, 6. Looks like I'm going to end up with a formal charge of a +1 there. Okay, so by putting a double bond in there, yes, we've given boron an octet, but we've totally fouled up the formal charges here. So that's why, from an energetics perspective, boron is actually perfectly happy taking an incomplete octet. Okay, but as far as when that happens or doesn't happen, boron is really the only element we're going to run into on a regular basis that will do this. Okay, otherwise, for anything without a hydrogen, you're trying to get an octet to it. Okay, and again, if it's something that is row 3 or beyond and it's the central atom, you can even get more than an octet to it. All right, any questions about that, guys? Those are your two sets of exceptions that we sometimes think about. And again, we can use those exceptions as a means of trying to minimize formal charge. Questions?
I have one question.
Please go ahead.
So for the fluorine that you did, that's on the right side.
Yeah.
You put 7 electrons, minus
Mhm.
6.
-6, yeah.
Well, wouldn't it be 8 because of the double bond, and then like
Okay, let's
7
take
minus 8?
yeah, let's take a look at that. So here's the rule. We're going to cleave the bond, right? So in terms of getting that number, that 6 over there, now where the 7 comes from, that's the number, that's the group number of fluorine, right? Fluorine's in group 7A, so we know it's bringing 7 electrons to the table, right? But now what about the 6? Where does that come from? Okay, so remember the non-bonding electrons, these guys that are these lone pairs around the fluorine, they belong exclusively to that fluorine, so we add them up. So we get 1, 2, 3, 4. Now look at the bond. Now if I cleave that bond right down the middle, what that means is that boron gets half the electrons and fluorine gets the other half, right? So each of those bonds is 2 electrons, isn't it? So if I have a double bond, that's 4 electrons. Whoops. But if I cleave that bond down the center, fluorine's going to get 2 of them, boron's going to get the other 2. Okay, so now if I count them up, I have 1, 2, 3, 4, go to the bond, and then it becomes 5, 6. All right, because half of that double bond goes to the fluorine, half of that double bond goes to the boron. And the same is true even with the single bonds like this. If you calculate a formal charge now for that fluorine there, okay, all the lone pairs belong to the fluorine. You have 1, 2, 3, 4, 5, 6 of them. Okay, plus 1 more that comes from cleaving that bond in half. The bond is 2 electrons. 1 goes to fluorine, 1 goes to boron. So you see how I calculate that?
Yeah, thank you.
No problem. Any other questions, guys? All right, that's good for today. So I think what we're going to do is get that extra Friday quiz, and guess what that's going to be on? I don't think there's going to be any surprises there. Focus in on those Lewis structures. Get in there and practice those, guys. So that last Friday quiz looks like it's going to be on Lewis structures primarily. All right, that said, we will see you guys next time.